Yeah, hey, hi there. So I'm the armchair mathematician. So I'm doing a bit of a rebranding. So we went from the origin to this channel. So instead of going for a more animated way of teaching math, I'm gonna go with a more amateur and more straightforward way of teaching you guys with pencil and paper. So the first thing we're gonna be talking about in this channel is topology. So what's all the fuss about topology? So if you guys haven't known by now, topology is my main field of study. I'm studying abstract differential geometry and algebraic topology. And the ultimate paper that I'm making over the next 4 years is going to be about abstract differential geometry. And so I wanted to give you guys a taste of what topology is. So I know some of you have came from my other channels, and I already gave you guys a taste of topology on that channel, which is Fanboy Mathematics. But here I'm going to give a proper introduction to topology. So, topology is the study of spaces that we can bend. So, one way to think about it is paper itself. So, what we can do with paper is that, or with what we call topological spaces, which is the main thing we study in topology, is that we can bend them, we can stretch them. Of course, I can't do it with paper, but you can do it with a rubber band. So, something like this. You can bend it, you can stretch it, you can twirl it around, but the thing you can't do is rip it or take away a subset from it. So for this video, I'm expecting you guys to know a little bit about set theory, about how we construct sets, basic operations in sets such as intersection and union, and things like that. So let's get right into it. So right off the bat, you guys are going to get confused when mathematicians talk about topologies and topology. So topology is the branch itself, the name of the branch that we study. And topologies are a special type of object we associate with sets to form what is called a topological space, which is that rubber band I showed you guys a while ago, or the sheet of paper that I'm writing on. So let's begin with the formal definition of what a topology is. So let X be a set. And this could be any set. It can be the integers, it can be the real numbers, it can be, hell, it could even be the quaternions, it can be even the octonions, the sydeinions, it can be any set. It doesn't need to be ordered, it doesn't need to have structure in the first place, it just has to be a collection of objects. Hell, it could even be just the set containing this pencil, and that we can construct a topological space from. So, a topology. So it's important to make this distinction. The object itself versus the name of the branch that this object is studied under. So a topology is a collection, also to say a set of subsets. I'll call them U, no, not this type of U, U in X, such that, so I'm gonna denote a topology by this symbol. You can call it tau. This is actually a special typesetting in LaTeX, which is the primary software we mathematicians use to write papers and render mathematical equations. And this is called mathcal T, capital T. It's a special type of written T. All right, so this is my denotation for a topology, which is a set of subsets from X, so a set of elements from X, or a set of elements from the power set of X, such that 1, X, and the empty set, or the null set, is inside T. And now I'm not using the subset notation here for this one, albeit we can say these guys are elements of T. Alright, so here's another thing you guys may get confused about when studying topology. When they say it is an element of the topology. So what we mean by that is that it is simply a member of the topology. It is inside the topology. Alright? We aren't saying that it's an elementary object inside the set. It is simply a part of the topology. Alright, so the topology, which I denote by T. So the first condition for topology is that the set itself, X, is inside T, and so is the empty set. They're both inside T. So the second definition, or the second requirement for topology, is that arbitrary unions of open sets are called open. So right off the bat, every element of T, every possible subset that is inside T from X is what we call an open set. So for the time being, abandon your notion or your intuition about open sets being, oh, it's an interval running from two numbers A to B. Right now, don't think about that. Just think that an open set is something inside a topology of a set. So two arbitrary unions of open sets are open. So we denote by this symbol that the union of any of these sets inside X is inside the topology. So let's say A, B, and C. I have subsets A, B, and C in X. If I want to construct a topology on X and I say that A and B and C are open sets, A, B, and C needs to be part of the topology. They need to be inside the topology. Alright? And right away, when you construct a topology on X and only involve X and the empty set, we call this the discrete topology. Immediately every element of X is inside the open set. Alright? But let's distinguish those in a moment. So the third one is that arbitrary intersections of open sets are open. Alright, so now let's use a bit of index notation. So I'm going to index a set, or these open sets U, with an alpha at the bottom. So this alpha is not to denote anything else but an index. So U1, U2, U3, these can be placeholders, or placeholders basically, for any set that you can think of inside the topology or inside the set. Alright? And so I'll just put it here, alpha, and alpha, alpha, alpha. So any intersection of these subsets from X, if we say those subsets are open, then their intersection must also be inside the topology. Alright? And also their union. So if A, B, and C are open sets, the intersection between these three must also be inside T, the topology. Likewise, if I combine these sets into one singular set, let's say that A, B, and C comprises X. They're the only subsets inside X. Then if I take the union of each of these guys, if I combine every element from each of these subsets into one singular set, then that collection or that set is also open or inside the topology. So these are the three main axioms that govern topology. Alright? So these are the three main axioms that a topology must satisfy in order to be a topology. Alright, so let's make an example. So let's say X is the set containing the numbers 1, 2, and 3. Alright. So let's say I have the power set of X. Alright, and then I take its union with the empty set. And then union with X. This over here gives us a topology of X, all possible subsets of X. Alright, so let's start with 1, the set containing 2, the set containing 3, the set containing 1, 2, the set containing 2, 3, the set containing 1, 3, and I think that's it. Maybe even the set containing 1, 2, 3, but that would mean X is inside itself, which is just not allowed. So this here would form a topology as well. In fact, this over here is called the discrete topology. I was wrong a while ago. What I meant by X and the empty set only, that is the indiscrete topology. So every set X that you can possibly have can have multiple topologies defined on it. Special topologies that we define on that that set to form a topological space that's special in its own way. So think of a topology as not only our way of defining what an open set is, but it is also a way for us to distinguish one topological space from another, or is our way of building a topological space from the ground up. So notice that if I take any union of these open sets, I would get something inside the topology. So if I take the union of the set containing 1 and I take the the set containing 2, I get the set 1, 2, which is inside the topology. Okay, now let's take an intersection. I take the intersection of the set 1, 2 and 2, 3, and I get the set 2, which is inside the topology. If all of those conditions hold, or if for every subset inside the topology, or element inside the topology, or open set inside the topology, these conditions hold, this is the topology over X. And notice that every set contains the empty set, because of course you can just make up an extra slot and it wouldn't matter. Alright. So let's say I would want to take the intersection between 1, 3 and 2, the set 2. I get the empty set because 2 is not inside 1, 3, and neither is 1, 3 inside the set containing 2. So because it's part of our topology, it's closed basically. So another way of rephrasing it is that 1, the condition is that X and the empty set is inside the topology. 2, the operation, or it is closed under arbitrary unions. And 3, it is closed under arbitrary intersections. Alright? So, what other more concrete examples are there of topologies? So there's something called the standard topology on the real numbers. And the standard topology is our way of defining Euclidean distances, or we define it via this over here, what you guys were probably thinking about an open set. So think of it as the set of all open balls inside R centered at a point X of radius or span A to B. AB X in R. So this is an example of a topology. What I mean by open ball is that it's just an interval. So if I draw the real line over here, an open ball would look something like this. And this is A, B, and the center is at X. So all possible all possible open intervals or open balls in R generates a topology called the standard topology in R. Okay. So let's get on with the next concept, which is called a topological space. So what is a topological space? So topological spaces are spaces you can bend. Geometrically speaking, they are spaces you can bend, you can stretch, you can squeeze, you can, do whatever you want to do. You can think of it like putty, or you can think of it like a rubber sheet. That's why topology is also called rubber sheet geometry. Alright? And so, formally speaking, a topological space is a structure now. So now we're talking about structure. Primarily, X didn't have a structure here, and neither did the topology on X. But now, we're talking about a structure. So it's now X equipped with its topology. This is a topological space. If I have a predefined topology on a set X, and I put those two together and say the topology is associated with the set X, or it's defined over the elements of a set X, we suddenly say that the combination or the pair of those two objects is a topological space. And this is the crux of topology, the topological space. This is where everything that we may discuss from here on out concerning topology is going to be about. This is a topological space. So an example of a topological space is a sheet of paper, a flat sheet of paper. So one can think of this as I cross I. So it's like a plane. Another example is a sphere. which we also denote via S2. So notice the distinction between a sphere and a ball, because spheres and balls are two different terms in topology. The ball is the area or the volume inside a sphere. A volume that is bounded by the sphere, what we say. And the sphere is the very, very thin line of points at the edge of a ball. So if I cover this up and say there are points inside of the sphere, that's the ball. And it's closed because there's a boundary. Without a boundary, it is open. And likewise, like here, A and B are not included in this open ball. If I make it a square bracket and say A and B are included, it's now the set of closed one balls or closed balls in R. And that generates a different topology, to be honest. Alright, another example, which is frankly my favorite topological space, because not only is it interesting, but it is yummy in real life, is the torus, which we denote T2. And another thing you guys will learn in topology is to differentiate or give you guys concrete tools and know-how on how to differentiate between a sphere and a donut. Okay, what's so different about a sphere and a donut? Notice how if I have a cube, I can deform the cube into the sphere. I can stretch the cube. I can make it bulge out and it will become the sphere. And likewise, I can sharpen the edges, or I can make edges on the sphere and turn it into a cube. But one thing I cannot do is turn a sphere into a torus or a donut. It's the same term. Because this here has a hole, well, this one here doesn't have a hole. But that's going to be an argument we're going to make more rigorous in algebraic topology. So these are one of the fundamental spaces that we will study. There's also another interesting topological space which we call a Mobius strip. And you guys will probably know what this looks like. It's a strip of paper which I twist before connecting. And notice that it is a one-sided topological space in the sense wherein if I travel along the outer part, I will end up inside after one cycle. And it will take me 2 cycles of walking around or walking forward to get back where I started. Unlike a sphere where I only take 1 cycle to end up where I'm back or where I was. Alright. So these are geometric examples of a topological space. And each of these guys has a, well, primarily they don't have topologies associated with them, but once we put them inside a different topological space, they immediately have one. Alright? So there are spaces, or there are topological spaces wherein we are not concerned just yet with the topology, but just the global know-how or what we know about it, and what we can do and what we cannot do with it. So this is a small taste of topology. So right before I leave, the action of me being able to transform one topological space into another without ripping it or without taking away a subset from it is called a homeomorphism. Homeomorphism. So right now, you guys only know what the geometric version of this, but rigorously, it's a map, a continuous map from one topological space to another. But that's a topic for another video. So right now, this is a good introduction. I don't know if it's good to you guys, but I tried my best on this one. So this is a good primer, or at least this is my primer on topology. And it's all about shapes, disregarding distances, lengths, widths, all that stuff, radii. It doesn't matter in the world of topology. So with topology, our minds can roam free when it comes to thinking about objects. And funnily enough, us topologists can think of a coffee mug as practically the same as a donut.